Today we're spending day 2 or day 3, depending on what school year it is, talking about improper integrals and more specifically the direct comparison test. There's a whole lot of tests that we can use to determine whether or not improper integrals converge or diverge. And our book doesn't specifically talk about the direct comparison test. They actually put it into some homework examples. So that's why today, after last night, you had a homework example having to do with this. We're going to talk about the direct comparison test more specifically. And what the direct comparison test says is you have two continuous functions on your interval where you're taking the integral, and you have one function that is less than another one, and they're all going between 0 and one function, the other function. Sounds like this a little bit like the squeeze theorem to me. And so if the bottom function converges, so if the function that is smaller converges than the larger function, that also implies that the larger function is going to converge. And then if the bigger function diverges, that forces the smaller one to diverge. And hopefully this is going to make a little bit more sense once we go through some examples and how we're picking our functions and things like that. Okay, so use the direct comparison test to determine whether or not this integral converges or diverges. So this one is a lot more challenging in picking our functions. So we know cosine squared is going to range between 0 and 1. Since I'm squaring, I'm not going to go into any negatives. Now, if I divide everything by an x squared, we know that our cosine function, so this integral here, this function is less than or equal to the greater function. So we have a greater function here. Okay, so we need to figure out whether or not that function here converges or diverges. This integral, I should say. So this integral, remember that p test that we talked about. This, since 2 is equal to p and 2 is greater than 1, this converges by the p test. So my larger converges. I'm going to flip back real quick. My larger one, g of x, converges. So if the larger one, the function that's basically on top of the other one, converges, it forces this to converge by our direct comparison test. Okay, next one. Using the direct comparison test to determine whether or not this converges or diverges. Notice I'm not even trying to find the value of these integrals. I just need to know whether or not they converge or diverge. So what we're going to do is we're going to compare this to something. So we are going to compare this to, we're going to compare this function to another function. As we go to infinity, minus 0.00011 doesn't matter. So I take away anything that I'm adding or subtracting. And then what I also look at is I try and simplify this the square root of x squared, and that simplifies to 1 over x. Now I need to figure out which function is smaller and which one is larger. So this denominator is smaller than this denominator, which gives me an overall larger number. Okay, so smaller denominator, larger value. So now I know that this integral, grab my dx, is bigger than this integral. So now we need to talk about the one that we're comparing it to. Thinking about the one that we are comparing it to, what do we know about this? We know p equals 1, and therefore this diverges by our p-test. So this diverges by the p-test. So my smaller one diverges. So the function that's below, my function that's below this function diverges. It goes off to infinity, and I can't find the sum. Therefore, by the direct comparison test, the function that is larger also diverges by my direct comparison test. Now let's look at this. So again, we want to compare this 1 over 6 plus x squared to a function. We want to compare that, so take away the 6. I want to compare that to that function. Bigger denominator equals smaller function. Okay, I struggle with that a little bit. I don't know why I conceptually struggle with that. Maybe I'm missing some math somewhere in my education. But conceptually, for sometimes I really struggle with comparing these. So this integral is less than or equal to this integral. And so now let's talk about the one that we know something about. We know that p equals 2 in this case, so therefore this converges by the p-test. So therefore this converges by the p-test, so therefore my bigger one converges, the function that's on top. This function, when I graph this function is above this function. So that's going to force this function, the area of this, to also converge by my direct comparison test. Okay, last example. So our last example here. Let's do this one in green. Use the direct comparison test. Okay, so I could really look at this like, I could really look at we'll leave it as it is. So I'm going to compare this. I'm going to compare this function to take away the 7 to this function. Smaller denominator, same numerator, larger denominator equals smaller all over number. So I know that inequality is true. So now we need to look at what happened here. And I'm going to pull the 5 out. Now I need to know whether or not that converges or diverges. If you remember way back to the first slide of our lesson, the first example we did, I talked about here that I converge for all a's greater than or equal to 1. So going now back to this slide, this is really like saying so this converges, and that's more of just a known fact. Maybe we could say a is greater than 1. So therefore I know, taking the 5 out of the integral that we do have, by the direct comparison test. Man, I got lazy here at the end. Okay, few things I want you guys to keep in mind. You have to show me, there we go. You have to show me the inequality. You have to show me something about, and then something about this integral that I'm comparing our equation, our original one to, okay? And I'm converging, and then give me a reason. Notice how a lot of my reasons centered around the p-test, okay? And then you have to state your conclusion of the final one converging by my direct comparison test and stating that. I'll let you guys use DCT. I got lazy there at the end. If I get lazy, then I have to allow you guys to be lazy. I don't like allowing you guys to be lazy, but I just recorded another 26. I recorded a 26-minute video right before this that you guys watched the other day. Anyway, I'm rambling here. So that's the direct comparison test for you. Our book doesn't formally talk about it, but understanding what this is going to set you up for some success with us second semester. And this is our last video of the semester. Isn't that exciting? Anyway, okay, I will see you all in class.